Hello and welcome back. In the last lecture, we defined Taylor's method for approximating root of an initial value problem, not really approximating the function that we should be getting the solution, but approximating its values at various equally spaced nodes. So let's do some examples with respect to that. Let me start sharing my slides. Okay, so this is what we are going to do, but let's quickly review the Taylor method of order n. So this is our initial value problem. We will have either y prime equal to f of ty or dy by dt equal to f of ty. The variable t takes values from a to b and y of a is assumed to be alpha. So this is the initial value and therefore this is called the initial value problem. The Taylor method of order n gives an approximate solution to the above problem at equally spaced nodes which are ti, that is a plus ih. So it will be a plus h, a plus 2h, a plus 3h and so on, where h is the step size, which is b minus a, the difference of the length of the interval divided by capital N. So we are going to have the nodes from t naught to even all the way up to t capital N. Capital T capital N is the last node. So you will have n plus 1 nodes. That's the situation now. And the approximations are W naught is the alpha, which is the approximation for the value at y at a, and that is correct because that's given to us with this problem. And wi plus 1 is wi plus h times a function depending on ti and wi, where that function capital T of ti comma wi is given to be f ti wi plus h by 2 f prime ti wi plus dot 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 h power n minus 1 upon n factorial, the n minus 1th derivative of the function f ti wi. So this is the description of the approximations that we are going to get from using the Taylor method of order n. So let's now do some examples. So suppose we want to apply Taylor's method of order 2 with capital N equal to 10. So the order is 2, therefore we will have f prime and f double prime, and n is 10, so we will have 11 nodes to solve this particular problem. So you are given y prime is y minus t square plus 1, t goes from 0 to 2, and y of 0, the initial value is given to be 0.5. Since we will have to compute y prime and y double prime, y prime is already given. So we need to compute y double prime, which is f prime, which is really the d by dt of the function f of ty. F of ty is given here, y minus t square plus 1. This is f of ty. We want to compute its derivative with respect to t. That will be y prime, because you have to compute the derivative of y with respect to t, which is y prime minus 2t. This is the f prime, or this is y double prime, but we can simplify it further because y prime is already given to us, which is y minus t square plus 1. So we put that value of y prime, subtract 2t further, and finally we get y minus t square minus 2t plus 1. This is the quantity y double prime or f prime ty, if you wish. So then our capital T, remember the approximations are given by wi plus 1 equal to wi plus h, which is the step size, into some function. So this is that function that we now have to compute. By our definition, this function is f of ti wi plus h by 2 f prime at ti wi. And we have the values now. F of ti wi is this. We will replace y by wi. We will replace t by ti. And f prime is given here, y minus t square minus 2t plus 1. So we need to put those values there. F of ti wi is wi minus ti square plus 1. plus h by 2 in the bracket, we have written the f prime of Ti Wi. And by simplifying, we get this 1 plus h by 2 Wi minus Ti square plus 1 minus h of Ti. So this 2 here that we have for 2Ti and this 2 in the denominator, they get cancelled. Everything else from the f prime term comes here with the other term, which is f of Ti Wi, and you have 1 plus h by 2 as a factor for that. Okay, so now we are taking n equal to 10 and our interval is 0 to 2. So we will need to divide this interval length, which is 2, by n, which is 10. That will give us the step size. So we put those values there. We get h is 0.2 and Ti will be 0.2 into I, where I goes from 0 to 10. And then the method will give W naught is 0.5. That's the beginning value. That's the initial value. And Wi plus 1 is Wi plus h times T, capital T of small Ti Wi, which we have computed from the previous slide. And now we put the value of h and Ti. Remember, Ti is 0.2 into I, right? So Ti square will be I square into 0.2 square. So 0.2 square is 0.04, and you have I square, and here you have h into Ti. H is already 0.2 and Ti is 0.2 I. So you will get a 0.2 square here also, but I will be as it is. And further simplification will give you this quantity 1.22 Wi minus 0.0088 I square minus 0.008 I plus 0.22. A very neat formula, and we can compute some of the initial values. In fact, we can compute y. So W naught is given to be 0.5. We can compute W1, which will be an approximation for the value y 0.2. So we will have to put I equal to 1, I equal to 0. If you want to compute W1, then I is 0. So that will mean that this terms involving I square and the terms involving I will get cancelled. You just have W naught, which is 0.5. So we multiply by 0.5 to 1.22, which is 0.61, and you have to simply add 0.22 to that. So that gives you 0.83. This is the approximation for y 0.2. The next approximation can also be computed. This is 1.2158. So you have 0.2. So this y 0.2, which is W1, and the next one that we have computed, there should not be an equal sign. It should be an approximation sign, which is the value W1. Okay, and we can actually compute all the values because we have to just compute the 10 values. There is a table that we use to write down all these values. So remember, order is 2 and n is 10, and these are the values. Look at the errors. The maximum error is 0.042212, and for some initial values, up to the value at 1.0, so that would be W5. The W5 is away from the actual value by 0.007787. So for the first 2 digits after the decimal point, the values are same. If you look at 0.2, so W1, that is actually equal to the correct value up to first 3 digits. Okay, so even if we have taken order to be just 2, we have gone just one step beyond the Euler's method. And we are taking n equal to 2, with n equal to 10, or the step size is 0.2. If you take the step size to be 0.1, then of course, as we know, the order will be the same and the step size is smaller. Therefore, we will expect that the error is also smaller. We will see what happens in that. But let's remember that here the first time for 0.2, the error is 0.000701. Okay, so the numbers are the first approximation. W1 is equal to y of T1 for first 3 decimal digits, first 3 digits after the decimal point. Okay, so now suppose we apply the Taylor's method of order 4, keeping the same n, which is n equal to 10, and problem is also same. We don't change the problem so that we can later compute and compare how these various orders compare with each other. Okay, so we have to now compute y prime, y double prime, y triple prime, and y fourth derivative, which is to say that we need to know f, which we already know. We need to know f prime, which we have computed in the previous example. Now we need to compute f double prime, and then we will need to compute the triple prime of f. So f double prime is simply taking the derivative of the above quantity with respect to t, and that is nothing but the derivative of y is y prime, and then minus 2t minus 2, those are the derivatives that you get. Again, the value of y prime can be computed from the above equation, from the initial value problem. We put that value here and simplify it to get this to be the final answer, y minus t square minus 2t minus 1. This is the second derivative of the function with respect to t. Third derivative of the function, so you have to compute the derivative of the second derivative, which is good. So y prime minus 2t minus 2. That's what we are going to get. Y minus t square minus 2t minus 1, its derivative. That is y prime minus 2t minus 2, which is the same as the previous derivative. Okay, so this value is the same. We don't have to go again in, by putting the value of y prime and then computing the final value. So f double prime and f triple prime happen to be the same, of course, because f prime and f double prime don't change in the values other than constants. Okay, so all these values are the same, and now we compute the function capital T. So capital T, now it's a slightly complicated function because you have order is 4. So we have f, we have f prime, we have f double prime and f triple prime, and of course the corresponding coefficients, which are h by 2, h square by 3 factorial, h cube by 4 factorial, and then there is an error which we ignore. So this is capital T of TIWI, which we can further simplify and write it in this way. Let's not try to remember all these values. We will come back and forth whenever we need to cross check. But this is how capital T of small TIWI is. So there is what we have done is that we have taken most of the values involving h in the bracket, and whenever there is a common quantity in terms of Wi and Ti square, we can take it out. Okay, and the Taylor method of order 4 is this. It will give W naught equal to 0.5. The initial value will not change, and Wi plus 1 is Wi plus h capital T TIWI. So Wi plus h into this whole quantity in square brackets. This is picked up from our previous calculation of capital T of TIWI. Now we can put the values of h. H is again capital N is same, our interval is same, our initial value problem itself is same. So we put those values, n equal to 10, h equal to 0.2, and I will just write the final computation now, which is Wi plus 1 is 1.2214 Wi minus 0.008856 I square minus 0.00856 I plus 0.2186. This is the way to write the approximate values. Let's again compute first two values, and they are these. W1 and W2 for our Taylor's method for order 4 are these two values. Let's again put those values in the table. If you remember, the error for W1 itself was 0.0007 something. So the values for W1 and Y of T1 were correct up to first 3 decimal points. Now we are looking at order 4 and n equal to 10, and these are the values. All values are correct at least up to 4 decimal points. So by having gone to the order 4 method, the error that we got for order 2 in the very first non-trivial step, going from W0 to W1 is worse than computing all possible errors here. So just going from order 2 to order 4 has made such a big difference. Right? Let's again look at both these tables next to each other and compare those values. So as I told you, the value for W1, which for order 2 is 0.0007. The error was this, whereas the error here in the order 4 is 0.000001. Much better approximation. So order 4 is giving us a much better approximation compared to the order 2 method. Okay, so as high the order of the method is, the error is that smaller. Of course, the number of computations increases, because for order 4 we have to compute not just the derivative but the second derivative and the third derivative. For Euler method we did not have to compute any derivative because the function, which is y prime, that was already given to us. So by the number of calculations, the Euler's method is really the optimal one, but it is very simple minded. It doesn't take any error into account, and the error is in fact linear in H. Whereas here we will see that the errors are much better. Okay, so these are the two values that we have seen. These are the two examples that we have seen for various orders with the same capital N and same initial value problem. Now, suppose that after having done all this, there is some another point at which we want to compute the approximation of the solution. So what we have done using the Taylor method is that there are these 11 nodes and we have computed some good approximation for these 11 nodes to the function y, the solution of the initial value problem. Now, if there is a point which is not among these 11 nodes, so suppose we are looking at y equal to 1.25. Okay, so this y is between 1.2 and 1.4. Let's just go and check the errors. 1.2, we are going to use order 4. The error at 1.2 is 0.000023. And at 1.4, it is 0.000032. These are the two errors. Okay. And we want to compute the value at y equal to 1.25. So we have to use some interpolation. There is no other way. We know this function is approximated by at those points by, so now this is where we see the real need for interpolation. We don't know our function y, yet we want to compute y value at 1.25, and what we know is that at various other points y is approximated by these quantities with very good margins, with very accuracy up to 0.4 digits after the decimal point. And now we will use interpolation to compute 1.25 at this point 1.25 between 1.2 and 1.4. So our basic guess will be to use linear interpolation. There are these two nodes, 1.2, 1.4. There is this graph which we don't know, but we know at least the points on the graph, at least the approximate points. So join those 2 points by a straight line and then see what value is on 1.25. This is something which is very natural, but we have also the formula for the linear approximation. We use this formula and compute this value to be 3.3180810. Now this is, the true value is 3173285. So you see that we have lost our accuracy. Now the accuracy is available only for the first 2 digits after the decimal point. For both 1.2 and 1.4, if you remember, it was 23 and 32. So if you take the midpoint, the average error was roughly 0.000027 or 275, 0.0000275. And this error is 0.0007525. Although the values are correct up to only first 2 decimal points, but the 80 and 73 are so close to each other that you get one more zero in the subtraction. But yet earlier you had the the average error was 0.0000 275. So this is in the multiple of that error. This is about 30 times the average of the two errors, which were at 1.2 and 1.4, and therefore we need to improve upon this, and this is why we are going to use the cubic Hermite interpolation. Okay, so we have computed using our Taylor's method of order 4 the approximate values of the solution function y at various nodes. Now there is one more point in between these nodes, and we want to compute approximate value at this point. By linear approximation, linear interpolation, we are not getting a good enough approximation, so we use cubic Hermite interpolation. You remember that this Hermite interpolation agrees with the function values and also on the derivative values. So we need to compute the derivatives for y at those points, meaning the approximate derivatives. But y prime is given by some quantity, right? It is y minus t square plus 1. So y prime at 1.2 is going to be y at 1.2 minus 1.2 square plus 1. And then the approximate value can be computed because y 1.2 is the w1. We put the value and compute this, which is 2.7399640. And similarly, we can compute y prime at 1.4. So we now have approximations for the y values at 1.2 and 1.4. We have the approximations for the y prime values at 1.2 and 1.4. So we have the data required to compute the cubic Hermite polynomial, and the corresponding polynomial is this. It has a linear term here, it has the square term here, quadratic term, and this is the cubic term. You can write it in the nested form, and then it will be simpler to compute it. And the value at 1.25 is then approximately 3.3173571. You remember it was 3.175 something in the previous slide, and therefore the error is now 0.0000286, which is roughly the average of the errors. Remember, we had computed the average of the errors to be 0.0000275. So this is roughly of that order. Therefore, cubic Hermite interpolation is much better. This error is about 4% of the error obtained using the linear interpolation. So you see that the error has gone down by a factor of about 25. Much better error. Okay. So this improvement in the accuracy will justify the computations which are required for the Hermite method. Of course, we had to compute y prime. We had to compute some approximate values for the derivative using the approximate values for the function values. So there was a little bit of accumulated error there. Maybe there is a round off error and all those things. But even then, the linear interpolation does not give you as good an approximation as the cubic Hermite polynomial gives. Okay, so now we go to the error in Taylor's method before we complete our lecture today. So if you use Taylor's method of order n for getting the solution to our initial value problem, y prime equal to f of ty, a less equal t less equal b, y a equal to alpha with step size h. If this is the description of the method that you are using, then the local truncation error is big O of h power n. So the local truncation error is in the power of the step size n, h. Therefore, if I made a comment that if you were taking h equal to 0.1 instead of taking it 0.2, then you see that already since the h has reduced by a factor of 2, and if you are using the method of order 4, already you will see the error would reduce by a factor of 16, which is 2 power 4, 1 by 2 power 4. Okay, so this is how the local truncation error distinguishes the various methods. The Euler method, the local truncation error would simply reduce by a factor of 2. The Taylor method of order 2 will reduce the error by a factor of 4. But the method of order n will reduce the error by a factor of 16. And therefore, this is a much better method compared with the Euler's method. But again, of course, there are limitations and drawbacks to this method. One thing is that you have to compute these various functions and its derivative values and so on of various orders. Even though the error is of big O of h power n, the computations is a bit of a concern. So what we would like to do is to reduce the number of computations while trying to keep the error to the similar order. This is what we would want to do, and we will see a very nice method in our next lecture. Till then, it's time to stop. So see you soon. Thank you.